Lecture 6, Spanning Trees and Enumeration. Recap of previous lecture. Previous lecture we have discussed the basic properties of trees and distance. Content of this lecture. In this lecture we will discuss the Prüfer code, Cayley's theorem, counting of spanning trees using various methods including Matrix Tree Theorem. Spanning tree and enumeration, there are 2 raised power NC2 simple graphs with vertex set which are labeled from 1 to n, since each pair may or may not form an edge. Therefore, total number of simple graphs which are required or which will be formed is 2 raised power NC2. Now, out of these simple graphs, how many are basically the trees? How many are the trees? So, that is given by Cayley's formula. So, with the set of vertices which are labeled as from 1 to n, that is denoted by this symbol. So, then there are n raised power n minus 2 different labeled trees, and that is called the Cayley's formula. So, the total number of possible simple graphs of n vertices is 2 raised power NC2, and out of these graphs how many are basically different labeled trees which are labeled the vertices from 1 to n, they are n raised power n minus 2 different trees are there. That is given by Cayley's formula. Now, using Cayley's formula we can see that if there are 3 different vertices and we label them as 1, 2, 3, so how many different trees will be possible? So, 3 raised power 1, that is 3 different trees are possible. So, this is one possible tree when these the node 1 and 2 and 2 and 3 they have got an edge. In another possibility, if 1 and 3 and 2 and 3 they have got an edge. Third possibility, 1 and 2 and 1 and 3 have got an edge. So, there are 3 possibilities only with the labeled trees. Similarly, if we take a vertex set 4 vertices and they are labeled out of this set 4, then there are 4 stars and 12 different paths. In turn, they comes out to be 16 different trees as far as Cayley's formula is concerned, and so on. So, now we can see a pattern with the given vertex set n, and using this particular formula, that particular pattern is basically covered, that is n raised power n minus 2, and that is called Cayley's formula. Prüfer, Krichhoff, Euler and Rennie, they have found out the proofs. We are going to discuss all this in this part of this lecture. We will discuss a bijective proof establishing one-to-one correspondence between the set of trees with the vertex set n and another set of known size. So, given a set n, set on n numbers, there are exactly n raised power n minus 2 different ways to form a list of length n minus 2 with the entries in S. So, the set of list is denoted by S raised power n minus 2. We use S raised power n minus 2 to encode the trees with the vertex set S. The list that results from the tree is its Prüfer code. Let us see the algorithm for Prüfer code. So, the Prüfer code will produce a code of length n minus 2, that is these numbers a1, a2 and so on up to an minus 2. These numbers are drawn out of this particular set n, and so given a tree, this particular function f will produce a code, and that is called a Prüfer code. So, for a given tree there is a code which will be of length n minus 2, that is called a Prüfer code. So, the input to this algorithm is a tree with the vertex set S, which is a subset of this particular label n which is given. As far as this algorithm is concerned, at ith step it will delete the last remaining leaf, and ai is basically the neighbor of this particular leaf that will be noted down. This particular iteration keeps on iterating. Finally, it will terminate when there will be only one edge joining between two vertices remains, or you can also say a K2 graph will remain, then only the algorithm terminates with a successful Prüfer code of a label tree. So, let us see the different aspects involved in this Prüfer code algorithm. So, first we will see one aspect, that is how to generate a Prüfer sequence from a given label tree. So, that means we are given a label tree and we have to generate a Prüfer sequence S, and on the other side also, if a Prüfer sequence S is given, we can generate that unique tree which is label tree. So, there is one-to-one correspondence from tree to a particular Prüfer sequence and Prüfer sequence to a tree we can construct. Now, if that is the case, for a given tree we are going to produce a Prüfer sequence, and this sequence will be drawn from each element of this Prüfer sequence will be from 1 to n, and total length of this particular code S will be n minus 2. So, how many such sequences are possible? So, let us see that if the length of this particular sequence is n minus 2, that means there are n minus 2 different containers, and each element of this container you can fill it with the number which are ranging from 1 to n, that is the label of these vertices. Similarly, in the other container also we can replace or we can choose any of these n numbers and so on. So, that means n multiplied by n and so on up to n minus n times. If you multiply, that becomes n raised to power n minus 2. So, how many such sequences are possible? They are basically in this number, that is n raised to power n minus 2, and every sequence represents a specific label trees. So, how many trees will be there? That is, these number of spanning trees are possible. Now, we have to see this particular algorithm, that given a label tree, how we are going to generate the Prüfer sequence. So, the algorithm, the first step of the algorithm is find a leaf of a tree with the smallest label. This particular, that means whenever a tree is given, always there are two leaves that we have seen in the previous theorem. Two leaves whenever there is a in the tree. So, this particular assumption to find out a leaf is possible whenever a tree is given. So, find a leaf of t with the smallest label. So, having identified a smallest label leaf, what we will do? We will delete this particular leaf, and the neighbor of this particular leaf will be added to that particular sequence. So, we are building up that sequence. This particular step is repeated, we have to keep on repeating, iterate till this condition arises that our tree becomes only K2, that means only one edge connecting two different vertices basically is left out, at that time this particular algorithm will terminate. Let us see this particular example. Let us say this T is given to us and we want to generate a Prüfer sequence. So, first we have to see in this particular tree how many different leaves are there. This is one leaf, another leaf. So, there are 4 set of leaves, and out of these 4, this one is the leaf with a least value 2. So, what we are going to do, we will take this particular neighbor, that is this particular neighbor we are going to take it, and this will be removed, and the remaining tree, that is, let us say after one iteration, that becomes T prime, T minus the vertex which is labeled 2 will be deleted. So, this particular tree T prime will have how many other leaves? 3, 4, 5. There are 3 different leaves which are remaining, and the one with a least value is 3. So, 3 will be removed, but the neighbor of 3 is 7. 7 will be added in the sequence S. So, 3 also will be removed from this particular tree. So, 2 and 3 they will be removed. So, in the resulting tree there are how many leaves are there? 1, 2, 3 different leaves are there, and out of them the least value is 4. So, the neighbor of 4 is 6. So, 6 will be included, and now 4 will be removed from the tree, and the resulting tree will basically get 4 removed out of it. Now, the remaining leaf nodes will be 7 and 5. Out of them 5 is having the least value. So, the neighbor of 5 is 6. So, 6 will be added again. So, you see some of the vertices, some of the labels are repeated in the sequence S or the Prüfer code, and then we will remove it from. So, the resulting tree will be the T minus 2, 3, 4 and 5. So, the leaves which will be remaining is 6 and 7 in that resulting tree. So, out of 6 and 7 the least value is 6. So, it will be picked up, and the neighbor of 6 is 1. So, 1 will be put and 6 will be deleted. So, after that deletion there will be only one edge remains, which is connecting 1 and 7, and that is nothing but 2 K2. So, this particular algorithm will terminate at this end, terminate with a sequence S. So, if we count how many elements are there in this particular sequence, 1, 2, 3, 4, 5, and how many nodes were there? There were 7. So, that 5 is nothing but n minus 2. So, the length of the Prüfer sequence, as we have seen in the algorithm, that it will generate for a particular tree a Prüfer sequence of length, Prüfer sequence S of length n minus 2. Let us see why this n minus 2 is basically coming up as the Prüfer sequence length. So, in the observation we have seen there is no leaf node which is appended to that particular sequence S, and also we have seen another observation that every vertex V is added to S a total of how many times? Degree of that vertex minus 1 times. So, we can see. So, 6 is appearing twice. Why? Because the degree of 6, node number 6 is having 3. So, 3 minus 1, that is 2 times, that is the degree of this node 6 minus 1, that is 2 times it is repeating. Similarly, here the node number 1 is also repeated 2 times because of the same condition, that the degree of is equal degree of 1 minus 1 becomes 2. So, 2 times it is appearing. So, with these two observations, what we can see that for a given tree T having n different vertices or the labels and m different edges, since it is a tree, we know that this m is equal to n minus 1. Now, let us see how many terms are there in S. So, number of terms which will appear in the Prüfer sequence S is nothing but degree minus 1 of that vertex, and for all the vertices we are going to make a sum that will add up to the length of the Prüfer sequence. So, with this particular summation, if we sum the degrees for all the vertices, this is nothing but a handshaking lemma. This will result in twice the number of edges. Similarly, 1 if we add how many times? If we add n times, it will become n. So, 2m, if we substitute the value of m as n minus 1, so this will gives you the length as n minus 2. So, the length of the Prüfer code is n minus 2 that we have proved. So, before we go ahead, let us see that if you are given a labeled, if you are given a Prüfer sequence, how we are going to generate a labeled tree from the Prüfer sequence. Let us see the proof idea. Let us assume that the Prüfer sequence of n minus 2 length is given using these symbols 1 to n, then we are going to generate a unique labeled tree T. Let us assume that S contains a1, a2 and so on up to a n minus 2. Why? Because only the length of the code is n minus 2, and these values of ai is drawn from 1 to n. Let us see the steps of this algorithm, that once the Prüfer sequence is given, how we are going to generate a label tree from a Prüfer sequence of length n minus 2, which is having the symbols from 1 to n. So, the first step is to find out the smallest element x from this particular set of labels, that is 1 to n, which is not present in that particular Prüfer sequence S which is given to us. So, let us assume that it is that particular label S which is not present in S. So, join this particular element to the first element of S and delete a1 from S and delete x also from the set of labels. So, we will run two different sets. One set, let us call it as L, the other set is a Prüfer code, that is a1, a2 and so on up to a n minus 2. So, we will take this particular value of x and we will delete this x. Similarly, here the first element also will be deleted. So, the resulting list L of labels and that the sequence S will be after removing the element a1. So, now the next iteration will begin from this particular modified list L prime and S prime. Again we are going to find out a smallest particular label here which is not present in the modified sequence S prime, and we are going to join this particular element which is having the smallest label with the first element of S prime, and we add an edge, and then we will remove these two elements from this particular list. Again we are modifying, and we continue to iterate until two items remain in this particular L. Then these two items, when they will remain, we are going to add an edge, and we conclude generating a label tree out of a given Prüfer code. Let us take an example. If the Prüfer code, let us say 17661 is given, here we can see that length is 5 and the label set is L 1, 2 and so on up to 7. So the smallest label here is 2, which is not present in S. So what we will do? We will take the first element of S1 S, and we will add an edge between 1 and 2, then we will remove it, and that resulting lists S and L will be considered for the next iteration. In the next iteration, what we will see, that 3 is the label which is not present in S. So let us consider 3, and we are going to basically join it with 7. So 3 and 7 will contribute to add an edge, and now they will be removed from both L and S. Similarly, let us take the label number 4. 4 is not present in S. So 4 is the least label which we will consider, and we will add an edge with 6. So 6 and 4 will be placed, and now we are going to remove these two nodes from this particular list. So the remaining elements in list L, let us say the label number 5 is not present in 6 and 1. So 5 will be chosen up, and the first element in S is 6, both will be joining with an edge, and now they will be removed. Then we are going to consider the label number 6. 6 is not present in S, so 6 and 1 they will get an edge. So 6 will be removed and 1 also will be removed. Now finally we are left with 1 and 7. So 1 and 7 will be placed an edge, and we terminate. So when we terminate, we see that we have generated out of S, we have produced a tree. So given a Prüfer code S, we have produced a tree, corresponding tree, that we have already seen in the previous proof, that if let us say a tree is given, how we are going to produce the Prüfer code, and now we have seen given a Prüfer code, we can generate a unique tree out of that code. That becomes a Cayley's formula. So Cayley's theorem says that for a given set S, which is basically of containing the elements from that label n, so there are n raised power n minus 2 different trees. Let us see the proof of this particular theorem. Now this will hold for the number of vertices is 1. So let us assume that n is greater than 2. So now we will prove that this particular algorithm defines the bijection, the algorithm which we have seen earlier, that will define a bijection function f from this set of trees with the vertex set which is given as S to that particular set S raised power n minus 2 of the list of the length n minus 2 from S. that we have already seen, that if let us say a tree is given, how we can generate a Prüfer sequence of length n minus 1. So, we must show that for each Prüfer sequence a1 to a n minus 2, which is a member of this s raised to power n minus 2, that exactly only one tree with that vertex set satisfies this particular mapping function f, and we can prove this by the induction on n. Let us take the induction on n. When n is equal to 2, there is only one tree with the two vertices. The Prüfer code is a length n minus 2, that is length 0, and it is the only such list. When induction hypothesis, let us assume n is greater than 2. Now, computing ft will reduce each vertex to a degree 1, that means degree of v minus 1, and then possibly it will get deleted. Thus, every non-leaf vertex in T appears in this particular f of t, that is in the Prüfer sequence. Now, here we also see that there is no leaf appears in S, because recording of the leaf as a neighbor of a leaf would require reducing the tree to one vertex. Hence, the leaves of tree are the elements of S not in Ft. So, if Ft is equal to A, then the first leaf gets deleted is the least element of S which is not in A, call it as x, and the neighbor of x is A1. Now, we are given A, which is an element in s raised to power n minus 2, and we seek all the solutions to this particular mapping of T to A, and we have shown that every such tree has x as its least leaf and has the edge x A1. Deleting x leaves a tree with the vertex set S prime that we have already seen, and its Prüfer code is A prime, A2 to A n minus 3 and n minus 3 tuple formed from S prime, and so on. So, by the induction hypothesis, there exists exactly one tree T prime having the vertex set S prime that we have constructed and having the Prüfer code A prime. Since every tree with the Prüfer code A is formed by adding an extra edge x A1 to such a tree, there is at most one solution to Ft is equal to A. Furthermore, adding x A1 to T prime does not create a tree with the vertex at S and the Prüfer code A. So, there is at least one solution. So, that gets proved. Now, corollary, this particular corollary will count the trees by their vertex degrees. So, this is an application of a Cayley's or a Prüfer code or a Cayley's formula. So, given a positive integers d1, d2 and so on up to dn, they are nothing but the degrees of all n vertices, and if we sum up these degrees to n minus 2, there are exactly n minus 2 factorial divided by di minus 1 factorials, the multiplication of all for all i's. Let us see the proof. So, while constructing the Prüfer code of a tree T, we record x each time we delete the neighbor of x until we delete x itself or leave x among the last two vertices. Thus, each vertex appears how many times? This degree of x minus 1 times in the Prüfer code. Therefore, we count the trees with these vertex degrees by counting the list of length n minus 2, that is, for each I have di minus 1 different copies of I. So, that means a particular label is appearing di minus 1 times. So, if we assign subscript to these copies of I to distinguish them, then we are permuting n minus 2 different distinct objects, and there are n minus 2 factorial such lists. Since the copies of I are not distinguishable, we have counted each desired arrangement how many times? di minus 1 factorial and multiply for all different i's. Once each way to order the subscript on each type of label. Let us see through an example. So, let us see we are given the trees with the fixed degrees. Consider tree with the vertices 1, 2, 3 and so on up to 7 different vertices, and the degrees of these vertices are given as 3, 1, 2, 1, 3, 1, 1 respectively. So, let us use this particular formula to find out how many different trees are there. So, that will be n minus 2 factorial divided by all the degrees. So, we can use in this particular equation if we apply. So, n means 7, 7 minus 2 is 5 factorial divided by all these degrees minus 1. So, the first one is 3 minus 1, 2 factorial, then is 0 factorial, 1 factorial, 0, 1 and again 2 factorial. So, 5 factorial divided by that becomes 30. So, 30 different trees are possible. Now, out of these 30 trees, we can see here that only the vertices 1, 3 and 5, 1, 3 and 5, they are non-leaves, they will be the internal nodes. So, the deleting leaves will yield the tree on 1, 3, 5, and there are 3 such subtrees possible, where in the first tree we see that in the center the 3 is there, in the other one the center is 5 and the third one the center is 1. There are 3 different possibilities wherein these 5, 1, 3 and becomes the internal nodes. So, let us count them. There are 3 such subtrees by which 3 is in middle and so on. To complete each tree, we add the appropriate number of leaf nodes, leaf neighbors to each of these non-leaf to give it the desired degree. So, there are 6 different ways to complete the first tree here. So, 3 different labels are already used. How many more are there? 4 different labels are remaining out of this particular 7 labels, because 3 are already used. So, 4 are remaining. So, that means if we choose out of 4 these 2 labels which are going to be assigned to 1, so in turn it will, and then 2 will be attached to the 5. So, 4C2 that becomes so that becomes 6 different possibilities of this particular tree. Similarly, as far as this is concerned, there are 12 possible ways here in this particular case. Why? Because 6 is choosing these possibilities. Now, both the remaining 2 nodes, the remaining 2 different labels are not going to be attached to 5, but they are being distributed to 5 and 3. So, there are how many possibilities? 2 possibilities are there. 2 into 6, there are 12 different possibilities. Similarly, here it is also having same thing, that is 12 possibilities. So, total possibilities 12 plus 12 plus 6, that becomes 30. So, 30 different trees are being generated by this way. Now, counting the number of spanning trees in a graph, now we can interpret the Cayley's formula in another way. Since the complete graph with the vertex at n has all the edges that can be used in forming the trees with the vertex at n, the number of trees with the specified vertex set of size n equal the number of spanning trees in the complete graph on n vertices. Now, consider more general problem of computing the number of spanning trees in a graph. In general, G will not have much symmetry as a complete graph, so it is unreasonable to expect a simple formula as Kn, but we hope for an algorithm that provides the simple way to compute the answer when a given graph is G. Let us see in this particular example the same thing. So, if the graph is not complete graph, let us say a kite is given. So, this graph is called a kite. The name of this graph is kite. Kite is given, and now we have to count how many spanning trees are there. Now, if we observe that how many spanning trees, that means we can form the spanning tree without this diagonal edge, and we can form the spanning tree with diagonal edge. There are only two possibilities. So if we form the spanning trees without this diagonal edge, how many different possibilities are there? So that means these particular vertices are going to be attached with the edge, and one set of vertices will not have an edge. So there are only 4 different possibilities. Now when the spanning trees, where the diagonal is used, that also is having 4 possibilities. Why? Because there are 2 ends who are not going to get the edges. So you see that who are going to get the edges. So this is one possibility, this is another possibility, this is another, and so on. So there are 4 different possibilities. Total 8 different spanning trees is possible from this particular graph, which is called a kite. So let us see in this example how using a systematic formula we can basically do this. So it is clear that the spanning trees of graph G not containing E are simply the spanning trees of G minus E. That means if you remove that particular edge, that is nothing but a diagonal edge, and when we basically include that diagonal edge, so there are only 2 possibilities, and we can count these 2 possibilities, 4 and 4, that becomes 8. So now for that we are going to define an operation which is called a contraction of an edge E having the endpoint UV. So we can contract means we can join on a same end, and basically this edge will be removed. So for example, if we contract U and V as the same node, all other edges will be preserved. Can see all the other edges are preserved, and this particular edge will be removed. So this becomes G minus E, G dot E. Why? Because it is a contraction. We haven't removed, but it is a contraction. That means that edge is basically contracted. This is called contraction operation. So to count the spanning trees correctly, we must keep the multiple edges, like here this multiple, keep the multiple edges resulting out of that contraction. So with this we have basically come up with a recurrence equation, and this recurrence equation will help us in finding out how many different spanning trees will be there for a given journal graph G. So let us see the recurrence equation. That means if we remove that particular middle edge E, that we have seen the diagonal edge, when it is removed we have to count how many are there, and then when we contract it, then how many are there, and sum of them will become that total number of different spanning trees. So let us take this particular example. So if this is the graph, which is a kite graph, so when we remove this particular edge, so this will be the graph without E, and then this will be when we contract, then this will be graph when we have contracted the edge. And now if we count how many are the possibilities in this particular graph G minus E, we have seen there are 4 possibilities, and how many possibilities are there here? Again 4 plus 4 will become 8. So basically here the importance of the loop is not going to affect the number of spanning trees. So if we can delete the loop which is there in before we start, then also the number of spanning trees count will be correct. So that is why we consider always the connected loopless graph for computing the recurrence equation. Now we are going to see another very generic technique, and which is much faster in compared to the previous ones, and this method is called a matrix tree theorem, or it is given by the Krichhoff. So basically for a given graph, instead of computing the recurrence equation, we will apply this matrix tree theorem, and this particular algorithm which basically uses to compute the determinant, and this computation of the determinant of the adjacency matrix is basically quite efficient. Hence this particular algorithm will compute the number of spanning trees for a very large values of n, a much faster method. So, let us see how this all can be done. So, this matrix tree theorem is much faster because the determinants of n by n matrix can be computed using fewer operation than n cube operation compared to the previous methods. Also, the Cayley's formula also follows from the matrix tree theorem when G is equal to Kn, but it does not follow easily from this proposition that we have seen earlier. Let us take the example. So, in this example, how this particular method will quickly compute, that we are going to see. Now, let us see that this particular graph is given and we want to find out how many different spanning trees are there. We have already seen using the recurrence. Now, we have to see this particular matrix tree computation, how it does it. So, what we have to do, we have to find out, first we have to draw a graph, some matrix that is called adjacency matrix of this particular graph, and let us take this particular vertex as 1. So, here this particular vertex 1, 2, then 3 and 4, these are number 1, 2, 3, 4, 1, 2, 3, 4. Now, we will fill it up with the adjacency equation, that means whenever there is an edge we will place 1, if it is not then 0. So, between 1 and 2 we are going to place 1, 1 and 4 we are going to place 1, 1 and 3 we are going to place 1, and this becomes 0. Similarly, as far as 2 is concerned, 2 and 3 there is an edge, 2 and 4 there is an edge, 2 and 1 there is an edge, 2 and 2 there is no edge. Now, as far as 3 is concerned, 3 and 1 is an edge, 3 and 2 there is an edge, and all others not having an edge. Now, note number 4, 2 is having an edge, 1 is having an edge, and all others are not having an edge. So, this is the adjacency matrix of this particular graph. Now, what we are going to do is we have to multiply these values by -1. So, they becomes minus, wherever these symbols are there they becomes minus. Next thing is we are going to, instead of zeros in the diagonal, we have to place the degrees of that particular node. So, for example, the degree of 1 is 3. So, in the diagonal instead of 0 we will write down 3 over here. Similarly, as far as the degree of node 2 is 3. So, instead of 0 we are going to basically put 3. Similarly, the degree of 3 is 2. So, instead of 0 we are going to put 2, and similarly the degree of 4 is 2. So, instead of 0 we are going to place 2 out of it. Now, then we are going to compute the determinant or a cofactor of this particular matrix. So, this particular way, for example, -1, 1 plus 1, and then basically we have to find out this value, that is 3 minus 1 to 0, minus 1 0 2, we have to compute this value. Now, this becomes plus 1, so that will go out. Now, as far as this is concerned, this you can compute easily, and that will be basically the value becomes 8. So, 8 we have seen this particular graph has given 8 using recurrence. Now, this is very quite efficient. Why? Because a very big graph also we can convert in a form of the adjacency matrix, and then we will multiply by -1, and then all the different degrees of the vertices are being placed here on the diagonal, and then we will compute the determinant or of this particular matrix, and that determinant will give the number of trees possible here in that particular graph, and that is called matrix tree computation. So, let us see the theorem statement of a matrix tree theorem. Theorem says that given a loopless graph G with a vertex set V1 to Vn, let Aij be the number of edges with the endpoint Vi and Vj. Let Q be the matrix in which the entry of ij is minus of aij when I is not equal to j, that means there is an edge. So, we have to put minus of aij, and whenever I is equal to j, that means the diagonal elements we are talking about, there we have to place the degree of that particular vertex. Now, if Q star is a matrix which is obtained by deleting the row and the column of T of Q that we have already seen. So, we are going to get this cofactor, that is minus 1 times S plus T that we have already done, times the determinant of Q. So, this is how we are going to establish the matrix tree formula, matrix tree theorem, and we can solve this particular problem of finding the spanning tree on a given graph very efficiently using this particular matrix tree theorem. Conclusion: in this lecture we have discussed the enumeration of trees, Cayley's formula, Prüfer code, algorithm for generating the Prüfer sequence from label tree, generation of label tree from the Prüfer sequence, spanning trees in the graph, matrix tree computation, matrix tree theorem. In upcoming lectures we will discuss minimum spanning tree and shortest path. Thank you.